Okay, Precalc C, hello. This video is 5 or 6 days too late, but you will recall it's Wednesday morning right now. Last week on, well, not Thursday and Friday, so I guess it must have been Monday and Tuesday, we learned about linear dependence and linear independence. And this wasn't in the textbook, so you were kind of relying on me a little bit for education on this topic, but I think it wasn't too hard, hopefully. Then due last Thursday and Friday was a worksheet on linear dependence and linear independence with just 2 problems on it. And well, we didn't have time to go over it on Thursday and Friday, I thought, but it's due this week for homework tonight. So I thought I would make a quick video going over this, and it's optional, but actually I think I'm going to tell everybody to watch it because there's some interesting things that are about to happen that sort of tie together a lot of the things going on. So okay, without further ado, here we go. I think doing the problems, hopefully, if you understood the lecture from last week, I think doing the problems is not that hard. Of course, you can make arithmetic mistakes, but hopefully you don't. Okay, both the problems, here they are written up on the board. They're the same directions. You're presented with a set of three-dimensional vectors, and the question is, are these vectors linearly dependent or linearly independent? Okay, and the definition I gave you, which is, I think it's a good definition for beginners. There's a sort of a more formal definition out there, but okay, what I said is these vectors are linearly dependent if you can make one out of the other two. Okay, so let's see if we can do that. Let's see if we can make vector w, which I choose arbitrarily, out of vector u and v. And so now I'm going to ask the question, is there some number, a is or some kind of real number, is there some number of these vector u's plus some number of these vector b's which by taking a linear combination, a sum of scalar multiples of this vector u and v, I can make the vector w. And in class I encourage you to think of this question as asking sort of, do I really need vector w, or can I kind of make w out of u and v? Okay, right, well, that was the thinking. Now I think it becomes easy-ish for a few minutes, because this is a vector equation, and this vector equation can be interpreted as a system of equations. Well, I'm solving this vector equation basically, and to solve that vector equation, I solve this system of equations. That's what this is really asking. Equals -3, 5a plus 7 equals 4. Okay. And, alright, how am I going to solve this system of equations? Well, this is a system of 3 equations in 2 variables. So this is an overdetermined system of equations, so it may or may not have a solution. Well, what should I do? I'm not even going to bother putting it in a matrix. I will just, let's see, do I have enough space for this? Maybe not. I will just perform some operations. I will multiply row 1 by -1. For row 2, I will take 2 row 1 plus row 2, and I will replace row 3 with 5 row 1 plus row 3. And, okay, let's see what happens. Kind of concerned about space a little bit, but whatever. Yeah, okay, so that's a plus 7b equals -2. And here we get for -2b, if I did that right. And 4 minus 3 is 1. And here I get, boom, boom, -35. And 7 is -28b. And 10 and 4 is 14. So that looks kind of right. And alright, well, now I sort of already see that I can, well, I'll just do it. What now? I get a plus 7b equals -2. But here, by dividing through by -2, I get that b is -1/2. And, well, here I just also get that b is -1/2. This makes me very happy because it means that this system in fact does have a solution. And all right, I can even, get rid of this third equation by subtracting equations 2 and 3, and I can get rid of the first equation by replacing row 1 with -7 row 2 plus row 1, and this would be, I guess, just like row 2 minus row 3 if we're being really serious about all of this. What happens, I get 7 halves and 2 and minus 2 is 1.5. So I think A is 3 halves. Yep. So A is 3 halves. Okay, so this is me just sort of slowly and patiently solving this system of equations. And it turns out that it does have solutions. And therefore, the answer to my problem is, I'm going to kind of write small here because I want to save some space. The answer to this problem is that I solved this system of equations, I found my coefficients, and therefore I've just learned that if I take 3 halves times vector u minus 1/2 times vector v, that I do indeed get vector w. Okay, and therefore I've sort of answered my question. I can make vector w out of u's and v's. Vector w is a linear combination of u and v, and so my conclusion of this problem is that this set of vectors u, v, and w are linearly dependent. This is a linearly dependent set of vectors because I can make w out of u and v. Okay, and notice that it was, I said this in class, but I'll say it again, it was arbitrary that I tried to make w out of u and v, because of course, if the 3 vectors are, well, at least in this normal kind of case, if the 3 vectors are, if w is a linear combination of u and v, then of course I can also, let's multiply through by 2, say, and I get 3u minus v equals 2w. So I might also very well express v as v is just 3. No, I guess I don't want that. I want everything to be positive for some kind of reason. So I'll just do this. I'll add that over. So what is u? U is in fact just 2/3 w plus 1/3 v. Okay, and of course, I guess the point of this is that you can just do algebra 1 and you can solve for vector u in terms of w and v, and you can solve for vector v in terms of u and w, and so there it is. Let me just confirm that I didn't do anything horrible. I did not. Okay. So that seems to be sort of all there is to it, and this is all I talked about in class. Take the 3 vectors, set up a system of equations with scalar multiples, solve the system of equations however you like. If it has solutions, it means that the vectors are linearly dependent. Okay, what we didn't have time for in class, and what I usually do, in the subsequent class when we go over this worksheet, is to kind of talk a little bit more about the geometry of what's going on. And this is like easy to do live when you have 3D objects that you can manipulate and move your head around and sort of change perspective on. But it's very difficult to do with picture, but I practiced and stuff for this video because I'm a super teacher. So, alright, I now ask you, what is the sort of geometric significance of the fact that u is 2/3 w plus 1/3 v? What does it really sort of mean about these 3 vectors to say that u is just a scalar multiple of w and v? Now, some of you might find this kind of obvious. If you can make u out of w's and v's, then u lies in the plane of w and v. Okay, and let me sort of try this now. I'm going to draw a 3D coordinate system. That's my origin. Here's x, and here's y, and here's z. I've never tried to draw this picture before, except for 10 minutes ago. And now, let's see. Now I will use blue and purple to draw w and v. Okay, so what does vector W look like? Okay, well, maybe, it looks like that, let's just say. And maybe vector V looks like this. Okay, great. So that's sort of like, one W and one V. All right, well, what I now want to draw a picture of is all linear combinations of W and V. In other words, what happens if I ride the V train some sort of arbitrary number of times, and I ride the W train, some arbitrary number of times? Where do I end up? Well, keep in mind that we also need, to consider not just, right, any of these W's, right? So I want to I'm sort of imagining now kind of all possible ways of riding, of adding some number of W's. Okay, I think this picture is kind of nice. I've never seen anyone try this before. And riding all possible kinds of V's. All right, look at this. It's kind of pretty art or something. Hopefully it's helpful. What I'm trying to sort of convey here is that if you allow me sort of any number of W's and any number of V's whatsoever, here I'm depicting only positive scalar multiples of W and V, but of course negative too, then where do I end up? Well, I end up kind of like in a plane. And the plane is all of those scalar multiples. Okay, and there's even a sort of a term for this, but I guess I don't want to kind of overload you with too much vocab. So I'll just say what I've tried to draw here is all possible, a picture of sort of all the possible points that you can get to with linear combinations of W and V. Or you can think of it as a picture of all the sort of vectors which are linear combinations of W and V. And the answer to that question is, it's the plane that is determined by those two vectors. If you give me two three-dimensional vectors, then there is one and only one plane that goes through those two vectors, and that's precisely the linear combinations. And okay, the reason why I wanted to get everything positive is so my picture would be more kind of beautiful or whatever. So what is this vector U? Vector U is 2/3 W plus 1/3 V. And so, if I want to draw a picture of U, well, it's going to be kind of small, but yeah, it's going to be sort of 2/3 of a W plus 1/3 of a V, and so sort of what I end up with is like that vector there. But the crucial thing is that this vector U lies in this plane, of course. Because by taking linear combinations of W and V, I always stay in that plane determined by W and V. Okay, so this is a very long-winded way of saying something that for some of you might have been immediately clear, but for others perhaps not, that geometrically, if U is a linear combination of W and V, then U is in fact coplanar with W and V. And so what we've really determined sort of geometrically is that these three vectors are coplanar. That's another way of interpreting what's going on here. That U, V, and W are coplanar. Okay, good. Holding that kind of back for a second, I will now go over here to just do number 2. So it's the exact same question that we're being asked. Is there some number of U, so -149, plus some number of V's, 361, which will give me 11, -2, -5, which will give me vector W. Okay, and once again, this gives rise to a system of equations. -a plus 3b equals 11. 4a plus 6b equals -2. 9a plus b equals -5. Okay. And, alright, well, I guess I can just go ahead and solve this system of 3 equations in 2 variables. Alright, once again, I'll multiply this first row by -1, For this, I'll do 4 row 1 plus row 2. And here I'll do 9 row 1 plus row 2. Okay, trying to squeeze this in. Gives me a minus 3b equals negative 11. I don't know why I didn't just convert to a matrix. I guess I just didn't feel like it. But you can also convert to a matrix. Maybe that's easier or something. Anyway, boom, boom, 12, no. Yeah, 18b, I guess, yeah. 18b equals 9. And, let's see, and now, zoom, zoom, 28b equals 6. Alright, well, I'm starting to feel now that this is just not going to work. Because I have a minus 3b equals negative 11. Here I have b equals 1/2 by dividing through by 18. But here if I divide through by 28, I get, let's see, 6 over 28 is like 3 over 14. And so I just get like this, right? So 14. So that's just bad. And okay, maybe there are sort of some more beautiful ways to do this problem. But I think already, what did I do in my paper? Oh, have I done something terribly wrong? 1842. Hold on, 4. Oh, I did something terribly wrong. Oh, terrible video. Good thing I have an answer key. So prepared, best teacher ever. I forgot to multiply by 4. So 44 minus 2 is 42. And yeah, I just completely made horrific errors in system of equation solving. But it's not too late. Bum 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 bum. Whoa, what's going on? 9 of these and this. 27 to 1 is 28. 99 minus 5 is 94? Whoa. Okay, so I made 2 big mistakes. Let's just pretend that didn't happen. So now, okay, so I have some more work to do, I guess. What now? How many times does 18 go to? I think 42 is actually just 7 times 6. 6 is just, that's just 3, right? 3 times 18 is 42. Well, yeah, just no. So sorry, 3b. Just divide both sides by 6, I guess. Oh man. Don't lose faith in me. I know arithmetic. Divide by 6, yeah. And okay, what can I divide by here? I have no idea. I guess just 2, right? Yeah, because half of 94 is 47. So all right. I mean, yeah. I have this. Still, I am at the same place. The place I am at is, dude, this system of equations definitely does not have solutions because b cannot be 7/3 and 47/14 at the same time because 47/14 is just not 7/3. Okay, I'm gonna wrap up this video quick while I still have my wits. Do I want to put the effort in to make this beautiful? I guess I could. That would mean, what would I want to do? I guess I would multiply by 14 here. I think that's what I did on my paper. Yeah, I sort of multiplied this by 14 and this by 3. Let's just do that. So what do I get? A minus 3b equals negative 11. And here I will replace row 2 with 14 row 2. So that's, okay, I'm going to lock in now. That's 42b equals 14 times 7 is 70 and 28. That's 98. 70 and 28, yeah. And now here I'm going to multiply by 3. So it's 3r3, and that gives me 42b equals, this times 3 is like 144. That's just true. No, what? 140? Is it not 144? Let's try again. What is 3 times 47? 120 and 21, so it's 141. Oh my god. Oh, of course, because yeah, 9 less than 150. That's what I meant to do. Alright, well now, finally, I get a minus 3b equals negative 11. And, okay, I'll just subtract, right? So here I get, I can divide this row 2 back through by 14. But before I do that, I will take negative row 2 plus row 3. And, well, now I get 43. I get 0 equals 43. Okay, all I am doing here is sort of maybe showing off or something, and maybe wasting time. But the point is that even already back here, you can tell that this system of equations has no solutions. And I just finished it off by taking the Gaussian elimination all the way. 0 is just not 43, that's just false. So there's definitely no ordered pair A comma B which will satisfy this system. And therefore, if there's no A and B which will satisfy this system of equations, that means there's no pair of coefficients which will satisfy this vector equation. And that means that it's not possible in this case to express W as a linear combination of U and V. And therefore, it means that in this case, U, V, and W are linearly independent. Linearly independent. Okay. Good, good, good. That was a little bit of a struggle. Okay, now comes the sort of exciting conclusion to all this, which is, what is the significance of this geometrically? Well, now you might be realizing, okay, well, if these three vectors are linearly independent, then what that means is that it's not true, contrary to this picture, it's not true that I can make one vector out of the other two. And so what we see now is that these three vectors are not coplanar. Okay, so this, at least in the three-dimensional case, barring some kind of weird exceptions, assuming the three vectors are not the zero vector and none of them is a linear combination, none of them is a scalar multiple of the other. If you give me three non-zero vectors such that none of them is a scalar multiple of the other, then everything I'm about to say right now holds, which is that this question that we're asking is really kind of a question about the relationship between these three vectors. Alright, and finally, and someone even mentioned this in one of my classes, this entire conversation now can be reframed in terms of a volume conversation. Because we learned that the determinant can be interpreted as the volume of the parallelepiped formed by the column vectors of that matrix. And so, keeping in mind this sort of geometric understanding of the 3x3 determinant, I can look over here and I can say, all right, well, what does it mean if, what kind of parallelepiped is formed by three vectors W, U, and V if U is in fact coplanar with W and V? All right, well, I think everyone can see that this parallelepiped, in fact, is like a flat parallelepiped. If the third vector, U, is actually not going sort of up off the plane determined by W and V, then in fact the parallelepiped determined by U, W, and V is flat and has zero volume. Whereas here, since these three vectors are linearly independent, since W, for example, is not in the plane determined by U and V, W is coming up, out. Therefore, the parallelepiped determined by these three vectors will have non-zero volume. And so there is a faster way to do this entire problem, which is, this is a sort of alternate way of doing number one. You could take these three vectors, U, V, and W, -1, 2, 5, -7, 12, 7, and 2, -3, 4. And, okay, based on our old understanding, I should interpret this 3x3 determinant as the volume of the parallelepiped determined by these three vectors. And this, I promise you, is going to be 0. And since this determinant is 0, it means that the parallelepiped has 0 volume, which means that the only way for that to happen is if the parallelepiped is flat, which is to say that one of the vectors is in the plane determined by the other 2 vectors. And that is a way of testing kind of sort of immediately that these 3 vectors are linearly dependent, which is what we saw. Whereas over here, for the second problem, if I were to take these other 3 vectors, -1, 4, 9, 3, 6, 1, 11, -2, -5, and stick those 3 vectors into a matrix and ask for that determinant, as we've seen last week, the interpretation of that determinant is the volume of the parallelepiped determined by those 3 vectors, and that we would see that this is not 0. And that tells me that this parallelepiped has a real volume, and that tells me that the 3 vectors are not coplanar, and that tells me that these 3 vectors are linearly independent. Okay, so this gives me yet another interpretation of the determinant. The determinant is just kind of all over the place. Here's sort of another way of understanding the determinant. It's a kind of, at least in the 3D case, it is a test for coplanarity of your 3 vectors. If the determinant is, if you give me 3 vectors and you ask for the determinant of that matrix, and the determinant is 0, those 3 vectors lie flat all in one plane. And if they're not 0, then the 3 vectors are not coplanar. In fact, they're linearly independent. Okay, of course, there's still sort of some work to do. This is not quite actually the shortcut that you might think, because I will ask you in the future if the set of vectors is linearly dependent, to also give the linear dependence relation. So I still do want you to find the scalars. So if you get 0, it means that you still have to sort of, I think you still have to solve this equation. But if you get that the determinant is not 0, then you know that they're linearly independent. Okay, good. That's it. I think this was way too long. Hopefully you watched on 1.5 speed.